This project has just come to an end, and I'm not going to go through the first 2 years' worth of work. I'm just going to jump straight into really what we've been bringing together in the last year. It is 10 minutes, 15 minutes maximum, so I'm afraid if I've left anything out, my apologies to any of the partners. You can see there are 5 universities, and there are 10 industrial partners that have taken part in this. So, what we've been doing over the full length of time, we've been using a recirculating flume in Liverpool. One of the issues with that is the fact that it's got a high blockage ratio. The advantage of it, of course, is you can condition the flow, so you can put a profile into it, you can add waves to it. More recently this summer, we went down to Inseen under the Marinette funding, and we did some work in the tow tank there. Obviously, very low blockage, so we were able to actually get some more data without the problem of blockage correction. What we've been doing is we've done basic flows on that. We did some wave interaction with it. We did yawed flows. We also did an offset blade, so that if there was a fault within any feathering mechanism, such that one of the blades was left off, then we've also got data on that. So the modelling we've been doing as well, then that's followed with this. We're using the ANSYS program. The blades are Wortmann. It's quite a high twist, and there's also quite a large route towards self-start. The yawing mechanisms we did plus or minus 10 degrees and 20 degrees for this, and also aligned. So I'm not going to go into the full details on that. Some of the wake measurements we got then from Liverpool, the 2 figures on the left are the horizontal contours, one of the settings. The ones on the right then are the vertical. Now, the left of both the horizontal and the vertical are where there's no waves present. So you can see an approximation for the wake. The 2 right-hand figures, though, are where there's a small wave present. So there's a bit of interaction then with the wake. As you might expect, there is an increase in mixing with the presence of a wave, which reduces the wake down. And as you can see from the curves underneath, there's an increase within the turbulence as a result of the wave. So we know then there is a benefit to the waves in so much as it'll reduce the wake. That's a benefit. So what we've done then is we've modelled the effect of waves, and we've aligned the turbine such that it's out of phase with a cresting wave, and it's also in phase. In this case, it's 2 rotations to be in phase with a crest. So the left-hand curve, or the left-hand points, give you the power range when there's no waves present. So as you can see, it's a fairly tight variation. Variation is due to some structural interaction with the support. The next one then, we have an out-of-phase rotation with the wave. You can see now that there is quite an amplitude in the amount of power that's being generated as the wave's going over the rotating turbine. The next one, or the third one of there, is when it's out of phase, but there's a profile flow. So you can see there's a slightly bigger amplitude. You also have a slight reduction in the power. The biggest one, though, is when it's in phase, you get this massive change in the power that's coming out. When it's cresting, you get your acceleration, it peaks with it, and you get that massive surge of power. When then you hit the trough of it, you get this dip into it. So we now know that there's massive variation when there's a wave interaction. When we look at it as a time basis, and these are all modelled on a transient basis, the lower set of curves are for individual blades. So you see it's a bit messy. So if we look at the total power, which is the axis on the right as well, the smallest of those amplitudes, that's when there's no waves, and you've just got a small amount of fluctuation due to interaction with the structure. Then you get a series of curves with an increasing amplitude to where you peak then with the in-phase rotation with the wave. And as you see, there isn't massive variations in the average. There is a slight drop depending on the wave condition, but it's those peaks and troughs that have to be ironed out on the production side. Again, not maybe a massive problem. We then look at the thrust that's going through the drive train, so the drive shaft is seeing these. Again, the top curves are the total thrust. As you can see, you're looking at about 300 kilonewtons on a 10-meter diameter turbine. It's these peaks and troughs that are the problem. So effectively, you need to design the shaft, certainly in this case, to be able to take those peaks, or you need to come up with a mechanism where you can actually alleviate those loads under those conditions. So it comes to the fact that this information then can lead into the design criteria. The biggest issue, when you have asymmetric loads that are or the shaft is being subjected to, the lower set of curves are the resultant bending moment as a result of asymmetric loading on the blades. So you can see it's fluctuating around the no wave condition. You've got a small fluctuation around about 30 kilonewton meters, but you get this massive peaking when you have a profile flow, as you'd expect. One blade is going to be subjected to very high loads. So you get this, which peaks at about 60, 70 kilonewton meters. They're large. Possibly also of relevance, if you look at the top curves, that's the angle at which that bending moment is, or the shaft is being subjected to the bending moment. And if you look at some of those, you have got the bending moment applying to one angle in the shaft, and very rapidly is dropped down then to 200. So you're going from a 350, so up right at the top, to suddenly then dropping down, bang, to a different angle. So this shaft is being subjected to bending moments that are all over the place. And that is a problem. And we haven't even included, well, I know some of the work that Southampton are doing recently, the turbulence based on top of this problem. So then we moved on to the fact of what happens if the flow is varying left to right fairly rapidly. If it's a slow change, you can yaw the turbine into it. What happens if it's fairly rapid? You're not going to yaw in on a rapid basis and have the thing flying back and forward. So we need to be able to look at what happens if you get that. Some of the data that was collected by the oceanography group in Ramsey Sound, we looked at that data and found that there was fairly rapid changes up to plus or minus 20 degrees from the aligned flow. So we looked at modelling that. Now, unfortunately, I only had the aligned case on this because I couldn't find the non-aligned flows. But effectively, we've done this and we've moved the turbine to the various angles we wanted to. We've modelled these in a transient nature, and we've looked at, one, what happens to the wake, and two, what happens to the characteristics of this turbine. So, we started off with the usual method. We went through a steady state side. The filled dots are an aligned case, and as you can see, there's a 20 up to a plus and minus 20 degrees offset. As you'd expect, the power, as you go further off axis, would drop down. Okay, there's nothing particularly unusual on that. So what we then said was, okay, is this correct? So we looked at doing then transient modelling, and we found actually the steady state underpredicts. If you've got, obviously, an aligned case with no major complications, steady state modelling is fine. When you start getting added complications, if it's yawed off axis, if the loads are varying, whatever's happening to it, the steady state has an increasing error in it. So you need to start going to a transient. So the 3 or 4 crosses on this curve is showing where the transient values are giving us. The triangles, or the three triangles there, are some of the data that we got out of the Marinette project, and you'll see they tie in quite nicely with the transient data. So the message we certainly would get from that is that if you're starting to complicate the flow or the orientation, the geometry, you should seriously consider a transient modelling on it. We looked at the thrust characteristics. Again, the dots are a line flow. The thrust, as it goes off axis, I think logically would go down, so that was fine. And then we did the same situation, steady state transient, with a couple of experimental bits of data. And what we find again is the transient will give us a better prediction of the loads. So if you relied on the steady state for some of these more complex problems, there would be issues. The bending moments, aligned cases, these are uniform profiles, so the only variation you're getting is because there's a structural interaction with the support. With the yawing, we're getting similar sort of peaks and troughs, but they're obviously offset. They're offset because now you've got the support structure is not fully, well, it's not behind all the blades. It's at an angle to it, so that's why there is this offset to where the peaks occur. Okay, so we've done this. What we did with regard to then trying to get these measurements, what are we going to do with the data? We've got a look at the condition monitoring. The turbine we've got has got various instrumentation in it, at the blade roots, the generator, and so we can pick up various issues with this. On the right, there's a drivetrain rig, where what we've been doing is putting in the signals we get from some of the measurements and the CFD, including fault data, and then we've been measuring off the generator signal to see whether we can pick anything up from that. So we've gone for a simple case where we've got a blade offset. In this example, and I've shown this before, we've got an offset thrust. And obviously, if one of the blades is offset, you're going to get a drop in power, you get a drop in thrust, you get a change in the torque, so you can pick up that signal to a point. So we've gone down the line then of looking at, in this case, it's torque, I'm afraid. So the first of these points is the rotational frequency. And we've changed the offset of a blade from 0.5 degree through to 6 degrees, so an increasing fault. So the first one is the rotational frequency of the turbine. The big peak is the frequency of rotation of the individual blades. So obviously 3 times the frequency of the rotational. Now what we've come up with is the amplitude of these 2 frequencies divided through the log of it and 20 to get this monitoring metric. And that's been analysed through 2 processes, and don't ask me about them. I know nothing about spectrogram processes and even less about EMD processes, so any questions, put them on a piece of paper. But the trends are there, so you've got an optimum case with increasing turbulence intensity that have gone into this. As you get an increasing offset, what you find is that you get this decreasing metric number. There's a 10% threshold being allowed, so that it reduces any false alarms. Over the 10% then, basically what you're saying, there is a fault within the system. And obviously the bigger the fault, the less of a metric you're getting, which is more of a problem. Now, using the 2 methods, it does function, it does work. Obviously, there's anomalies on the EMD, but it would still give an alarm. So effectively, it's one method of actually trying to identify that there is a fault by measuring the torque within the system. I think that is it. Yes. Okay?
This production is brought to you by the University of Edinburgh.